In mathematics, group cohomology is a set of mathematical tools used to study groups using cohomology theory, a technique from algebraic topology, analogous to group representations. Group cohomology looks at the group actions of a group G in an associated G-module M to elucidate the properties of the group, by treating the G-module as a kind of topological space with elements of representing n simplices. Topological properties of the space may be computed, such as the set of cohomology groups. The cohomology groups in turn provide insight into the structure of the group G and G-module M themselves. Group cohomology plays a role in the investigation of fixed points of a group action in a module or space and the quotient module or space with respect to a group action. Group cohomology is used in the fields of abstract algebra, homological algebra, algebraic topology and algebraic number theory, as well as in applications to group theory proper. As in algebraic topology, there is a dual theory called group homology. The techniques of group cohomology can also be extended to the case that instead of a G-module, G acts on a non-abelian G group, in effect, a generalization of a module to non-abelian coefficients. These algebraic ideas are closely related to topological ideas. The group cohomology of a group G can be thought of as, and is motivated by, the singular cohomology of a suitable space having G as its fundamental group, namely the corresponding Eilenberg-MacLane space. Thus, the group cohomology of Z can be thought of as the singular cohomology of the circle S1, and similarly for Z2, Z and P infinity. A great deal is known about the cohomology of groups, including interpretations of low-dimensional cohomology, functoriality, and how to change groups. The subject of group cohomology began in the 1920s, matured in the late 1940s, and continues as an area of active research today. Motivation. A general paradigm in group theory is that a group G should be studied via its group representations. A slight generalization of those representations are the G-modules. A G-module is an abelian group M together with a group action of G on M, with every element of G acting as an automorphism of M. We will write G multiplicatively and M additively. Given such a G-module M, it is natural to consider the submodule of G invariant elements. Now, if N is a submodule of M, it isn't in general true that the invariants in M, N are found as the quotient of the invariants in M by those in N. Being invariant, modulo N, is broader. The first group cohomology H1 precisely measures the difference. The group cohomology functors H** in general measure the extent to which taking invariants doesn't respect exact sequences. This is expressed by a long exact sequence. Formal constructions. In this article, G is a finite group. The collection of all G-modules as a category equals G, for all G and G and X in M. This category of G-modules is an abelian category with enough injectives. Sending each module M to the group of invariants Mg yields a functor from this category to the category AB of abelian groups. This functor is left exact but not necessarily right exact. We may therefore form its right-derived functors. Their values are abelian groups and they are denoted by Hn. The nth cohomology group of G with coefficients in M. H0 is identified with Mg. Long exact sequence of cohomology. In practice, one often computes the cohomology groups using the following fact. If is a short exact sequence of G-modules, then a long exact sequence is induced. The maps delta n are called the connecting homomorphisms, and can be obtained from the snake lemma. Cochain complexes rather than using the machinery of derived functors. The cohomology groups can also be defined more concretely, as follows. For n0, let Cn be the group of all functions from Gn to M. This is an abelian group. Its elements are called the n-cochains. The co-boundary homomorphisms are defined as the crucial thing to check here, as thus we have a cochain complex and we can compute cohomology. For n0, define the group of n cocycles as and the group of n coboundaries is in the functors extn and formal definition of group cohomology. Yet another approach is to treat G-modules as modules over the group ring ZG, which allows one to define group cohomology via ext functors, where M is a ZG module. Here Z is treated as the trivial G module. Every element of G acts as the identity. These external groups can also be computed via a projective resolution of Z, the advantage being that such a resolution only depends on G and not on M. We recall the definition of ext more explicitly for this context. Let F be a projective ZG resolution of the trivial ZG module Z. E.g., one may always take the resolution of group rings Fn equals ZGn plus 1 with morphisms. Recall that for ZG modules n and m, HOMG is an abelian group consisting of ZG homomorphisms from n to m. Since HOMG is a contravariant functor and reverses the arrows, applying HOMG to F termwise produces a cochain complex HOMG. The cohomology groups H** of G with coefficients in the module M are defined as the cohomology of the above cochain complex. For n0, this construction initially leads to a coboundary operator that acts on the homogeneous cochains. These are the elements of HOMG, i.e., functions phi n, g n m that obey the coboundary operator delta. Cn plus 1 is now naturally defined by, for example, the relation to the coboundary operator d that was defined in the previous section, and which acts on the inhomogeneous cochains, is given by reparameterizing so that and so on. Thus, as in the preceding section, group homology duly to the construction of group cohomology, there is the following definition of group homology. Given a G module M, set Dm to be the submodule generated by elements of the form Gm minus M, Gg, mm, assigning to M its so-called coin variance, the quotient is a right exact functor. Its left-derived functors are by definition the group homology. Note that the superscript-subscript convention for cohomology, homology agrees with the convention for group invariance, coin variance, while which is denoted co-switches. Superscripts correspond to cohomology H** and invariance xg, while subscripts correspond to homology H and coin variance xg equals xg. The covariant functor which assigns mg to m is isomorphic to the functor which sends m to z zg m, where z is endowed with the trivial g action. Hence one also gets an expression for group homology in terms of the tool functors. Recall that the tensor product nzg(m) is defined whenever n is a right zg module and m is a left zg module. If n is a left zg module, we turn it into a right zg module by setting ag equals g minus 1a for every gg and every an. This convention allows to define the tensor product nzg(m) in the case where both m and n are left zg modules. Specifically, the homology groups Hn can be computed as follows. Start with the projective resolution f of the trivial zg module z, as in the previous section. Apply the covariant functor zg(m) to f termwise to get a chain complex f zg(m). Then Hn are the homology groups of this chain complex. For n0, group homology and cohomology can be treated uniformly for some groups, especially finite groups, in terms of complete resolutions, and the Tate cohomology groups, Functorial maps in terms of cochains, connecting homomorphisms for a short exact sequence 0 The connecting homomorphisms delta n, Hn plus 1 can be described in terms of inhomogeneous cochains as follows. If C is an element of Hn represented by an n-cocycle phi, gnn, then delta n is represented by dn, where psi is an n-cochain gnm, lifting phi. Non-abelian group cohomology, using the G invariance and the one cochains. one can construct the zeroth and first group cohomology for a group G with coefficients in a non-abelian group. Specifically, a G group is a group A together with an action by G. The zeroth cohomology of G with coefficients in A is defined to be the subgroup of elements of A fixed by G. The first cohomology of G with coefficients in A is defined as 1 cocycles modulo an equivalence relation instead of by 1 co-boundaries. The condition for a map phi to be a 1 cocycle is that phi equals phi G phi, and if there is an A in A such that, in general, H1 is not a group when A is non-abelian, it instead has the structure of a pointed set. Exactly the same situation arises in the zeroth homotopy group, which for a general topological space is not a group but a pointed set. Note that a group is in particular a pointed set, with the identity element as distinguished point. Using explicit calculations, one still obtains a truncated long exact sequence in cohomology. Specifically, let be a short exact sequence of G groups. Then there is an exact sequence of pointed sets connections with topological cohomology theories. Group cohomology can be related to topological cohomology theories. To the topological group G there is an associated classifying space BG, whose fundamental group is G and whose higher homotopy groups vanish. The nth cohomology of BG, with coefficients in M, is the same as the group cohomology of G with coefficients in M. This will involve a local coefficient system unless M is a trivial G module. The connection holds because the total space EG is contractible, so its chain complex forms a projective resolution of M. These connections are explained in Chapter 2. When M is a ring with trivial G action, we inherit good properties which are familiar from the topological context. In particular, there is a cup product under which is a graded module, and a Kunath formula applies. If, furthermore, M equals K is a field, then H** is a graded K algebra. In this case, the Kunath formula yields, for example, let G be the group with two elements, under the discrete topology. The real projective space P infinity is a classifying space for G. Let K equals F2, the field of two elements. Then a polynomial K-algebra on a single generator, since this is the cellular cohomology ring of P infinity. Hence, as a second example, if G is an elementary abelian 2 group of rank R, and K equals F2, then the Kunath formula gives a polynomial K-algebra generated by R classes in H1. Properties. In the following, let M be a G module. Functoriality group cohomology depends contravariantly on the group G, in the following sense. If F(Hg) is a group homomorphism, then we have a naturally induced morphism Hn. Given a morphism of G modules Mn, one gets a morphism of cohomology groups in the Hn. H1 the first cohomology group is the quotient of the so-called crossed homomorphisms, i.e., maps F. Gm satisfying F equals F plus AF for all A, B and G, modulo the so-called principal crossed homomorphisms, i.e., maps F. Gm given by F equals M minus M for some fix MM. This follows from the definition of cochains above. If the action of G on M is trivial, then the above boils down to H1 equals hom, the group of group homomorphisms Gm. H2 if M is a trivial G module, the second cohomology group H2 is in 1-to-1 correspondence with the set of central extensions of G by M. More generally, if the action of G on M is non-trivial, H2 classifies the isomorphism classes of all extensions of G by M in which the induced action of G on M by inner automorphisms agrees with the given action. Change of group. The Hochschild-Serre spectral sequence relates the cohomology of a normal subgroup N of G and the quotient G, enter the cohomology of the group G finite groups G. From it, one gets the inflation restriction exact sequence. Cohomology of finite groups is torsion. The cohomology groups of finite groups are all torsion. Indeed, by Maschke's theorem, the category of representations of a finite group is semi-simple over any field of characteristic zero. Hence, viewing group cohomology as a derived functor in this abelian category, one obtains that it is zero. The other argument is that over a field of characteristic zero, the group algebra of a finite group is a direct sum of matrix algebras. While a matrix algebra is Morita equivalent to its base field and hence has trivial cohomology. History in relation to other fields. The low-dimensional cohomology of a group was classically studied in other guises, long before the notion of group cohomology was formulated in 1943–45. The first theorem of the subject can be identified as Hilbert's Theorem 90 in 1897. This was recast into Noether's equations in Galois theory. The idea of factor sets for the extension problem for groups arose in the work of Holder, in Issachur's 1904 study of projective representations, in Schreier's 1926 treatment, and in Richard Brouwer's 1928 study of simple algebras and the Brouwer group. A fuller discussion of this history may be found in 1941, while studying H2, Hopf discovered what is now called Hopf's integral homology formula, which is identical to Schur's formula for the Schur multiplier of a finitely presented group, where G, F, R and F is a free group. Hopf's result led to the independent discovery of group cohomology by several groups in 1943–45, Ellenberg and MacLane in the USA, Hopf and Ekman in Switzerland, and Freudenthal in the Netherlands. The situation was chaotic, because communication between these countries was difficult during World War II. From a topological point of view, the homology and cohomology of G was first defined as the homology and cohomology of a model for the topological classifying space BG as discussed in #connections with topological cohomology theories above. In practice, this meant using topology to produce the chain complexes used in formal algebraic definitions. From a module-theoretic point of view, this was integrated into the Cartan-Ellenberg theory of homological algebra in the early 1950s. The application in algebraic number theory to class field theory provided theorems valid for general Galois extensions. The cohomological part of class field theory was axiomatized as the theory of class formations. In turn, this led to the notion of Galois cohomology and étale cohomology. This is a large field, and now basic in the theories of algebraic groups. The analogous theory for Lie algebras, called Lie algebra cohomology, was first developed in the late 1940s by Chevalier-Ellenberg and Koszul. It is formally similar, using the corresponding definition of invariant for the action of a Lie algebra. It is much applied in representation theory, and is closely connected with the BRST quantization of theoretical physics. Group cohomology theory also has a direct application in condensed matter physics, just like group theory being the mathematical foundation of spontaneous symmetry-breaking phases. Group cohomology theory is the mathematical foundation of a class of quantum states of matter, short-range entangled states with symmetry. Short-range entangled states with symmetry are also known as symmetry-protected topological states.